Hi, and welcome to part 2 of the chapter 3 video on normal distributions. So at the end of the last video, we talked about ways to find more exact answers for normal probabilities, normal distributions. Also ones that don't require the use of 689599.7. So I'm going to just do some examples of this. And I'm doing this in live real person so that I can use tables and calculators so you can see this. So I'm not going to read the blue part first. I'm going to start with the red part. I'm going to show you how to do this on tables and with your calculator. Now, I might ask you to do either of those on a test. And you might be thinking, but I'm not allowed to calculate on the test, so let me explain to you how I might do that. So for a calculator question on a test, I might ask you something like, which of these calculator functions would you use for this problem? So you wouldn't actually complete the whole problem. It would just be something like a multiple choice, and you'd say, oh, well, that was the thing I would use if this was the problem I was going to do on my calculator. You might also be asked things like, what values would you plug into the calculator for this situation? So I might, for example, say, well, you're about to use the normal CDF button. What values would you then give it in order to complete this process? And I will show you an example of that when we get into the problem. And then I might ask you something to just use the calculator output. I might say, if your calculator gave you this answer and show you a calculator output, how would you interpret it? So you won't actually physically have to use your calculator, but you will have to know what you would do on your calculator. So know how to use your calculator, know how to do it by hand. Both of these are important and useful. So let's actually read the problem. Use both the table and the calculator methods to find the following. The length of a certain type of fish is normally distributed with mean 16 inches and standard deviation 4 inches. Now I'm going to leave that up there so we can refer back to it, and here's the actual questions. Part 1. What percent of these fish are between 10 and 13 inches long? Now, we're going to do this both in our calculator and by hand, and either way, I would highly suggest starting with a picture. And our picture doesn't have to be perfect, it's just to help us think. But we know that it's normally distribution, so that's the hill. And in the middle goes our mean, which is 16. You can see that right there. I'm not going to put the standard deviation on. It's really not important to the picture. And what I want is everybody between 10 and 13. If this is 16, 13 is somewhere to the left, and 10 is somewhere even more to the left. It doesn't particularly matter where we put them. What matters is that they go in the right order. I don't want 13 to be above 16. That wouldn't make any sense. And so what I'm looking for, if we remember, percent or proportion is area, and I'm looking for that area. So this picture goes with either the calculator version or the by hand version. And please note that even if you can't do the problem, this picture can get you partial credit, assuming there's a way to draw that picture. If it's, I don't know if they're hand tests or computer tests yet, so we'll figure that out. So let's do by hand first. By hand, we're going to use a table, but that table only does standard normal. So step 1, I guess step 1 should be kind of write out what we're looking for in math. I want, now we haven't officially gone over this, but P stands for percent. I want the percent of stuff that's between 10 and 13. And you don't have to write that if you don't want to. It's just going to help us see the next parts. Step 2 is to standardize this. I want to rewrite this statement, but instead of using X, which is generic whatever our data is, I want to change them to Z's, standard normal, the one that the book uses. And so I'm going to just take each of these important values, 10 to 13. Those were the values I cared about. So I'm going to come over here and I'm going to use the standardizing formula. And if we remember the standardizing formula, Z is X, which is the data, the number we care about in our problem, minus the mean the problem gave us, divided by the standard deviation the problem gave us. So in this problem, the first number we care about is 10. I'm going to take 10 minus the mean, which is 16, divided by the standard deviation, which is 4. 10 minus 16 is negative 6. When we divide by 4, we get negative 1.5. Now, because of how the table works, I'm going to actually call that 1.50 because the table always wants 2 decimal places, and I'll show you that in a sec. So, where we used to write 10, now we're going to write negative 1.5. And I would write the 0 there, but I'm out of space, so I won't. Now we have to do the same thing with our 13. In this case, our z is 13 minus 16 over 4. That's negative 3/4 or negative 0.75. It's already 2 decimal places, and I'm going to take that 13 and turn it into a negative 0.75. So that's the standardizing part. What we needed to do was take the values we cared about, 10 and 16, and turn them into standardized places. So we could redraw the whole picture. The 16 would become the mean of a standard normal, and if we remember, the mean of the standard normal is 0. I'm going to write these in red just to keep them separate. Our 10 became a negative 1.50, and our 13 became a negative 0.75. The rest of the picture stays exactly the same. I could redraw the whole picture, but it would look just like the picture we had with new numbers. So that's what we're looking for. And here is where now step 3 is go to the table. Now this table, as I believe I already stated on another video, is on page 698 and 699 of your book. And if we look, it says table A, standard normal, and it has a picture of a hill. Now, different books have different tables. What's important to notice on ours is that given a z-line cutoff, they're giving us always the area to the left, all the area to the left. So, I'm going to start by looking up the negative 0.75, the one that used to be 13. It doesn't matter which order you look it up on, but I'm just going to start there for reasons you'll see in a second. Now, here you're going to see our numbers are always one place after the decimal. Across the top is your second decimal place. So for negative 0.75, we're going to look for negative 0.07. And then we're going to go up to the column called 5. Putting those together, we get negative 0.75. So I'm going to go across, down, down, down. And where the row and that column meet, apparently someone's already done this problem, is 0.2266. So again, everything by the second decimal place, you look here. The second decimal place, you look across the top, and then you go down and over to see where they meet. Now, that number, 0.2266, is the area to the left. On our picture, that is this entire area. But notice, that's too much. I didn't want everything, I just wanted this shaded piece. I don't want that little piece of the tail. And that's where looking up the 10 comes in. I'm going to now look up negative 1.50, because that's what 10 turned into. Here's negative 1.5. The last decimal place is 0, and so our number is 0.0668, and that is again everything to the left of our number. So everything to the left, which is this little space here, of negative 1.5 is 0.0668. And we can see that what I wanted was the big area, but removing the little area and removing a subtraction. So our percent, our answer, is the 0.2266 minus the 0.0668. It would probably have been better had I lined those up stack one on top of the other since I wanted to do this by hand. And it turns out to be 0.1598. Now, honestly, I just put that into my calculator, but we could do that by hand if we really had to, right? So our answer, since it's supposed to be a percent, is 15.98%. I take the values that I care about, I standardize them. You can write the math or not, I don't care. Then we use the table to find each area that that number represents, and we combine them in some useful way. We subtracted this time. It's not always going to be a subtraction problem. It just depends on what we need. So it takes some logic and some practice to see what we need to do with our numbers. So that was by hand. Now let's see how to do this on our calculator. Because we're given the numbers and we want to find the percent, the button, as we went over last time, is normal CDF. And when you're given the normal CDF, you always are asked for the low bound of our shaded area, the high bound of our shaded area, and then the mean and the standard deviation. So in this picture, we want to shade everything between 10 and 13. That means the 10 is our low, the 13 is our high. So find the area between 10 and 13 when our mean is 16 and our standard deviation was 4. We put that formula into our calculator. Let's see how to do that. So we see right down here that yellow dister. We're going to hit second distributions, and normal CDF is number 2. And then I'm just going to put in those numbers I just had. 10, 13, 16, 4. Those exact numbers we just wrote out. We hit enter, and it gives us rounded 0.1598, which is exactly what we already got from the table. So you can see it doesn't matter which way we use it, it's going to give us the same answers. Now, that being said, it might occasionally give us slightly different answers. One might be 15.98% and the other might be 15.97%, or something just a little bit off. And the reason for that is when we run these, when we do that by hand, this time the 10 and the 13 turned into very nice numbers we didn't have to round. But if I had something like 13.7 and the standard deviation was 32, things might not turn out as well. And so we will always be rounding these z's to 2 decimal places. And that rounding, which is unavoidable, causes error. And so the calculator is going to give us the slightly more accurate answer, but they're going to be both very close, so it won't matter. So let's do a similar problem and see again how we do these two methods. Part B, what percent of these fish are shorter than 21 inches long? And again, I'm going to start with a picture. I don't care which method we use, I always love a picture. Mean is 16, and I want shorter than 21. Well, 21 is bigger than 16, so it's going to be somewhere over there. And I want shorter, this is the shorter side. So that's what I'm trying to get. I want to know the area of this shaded region. So by hand, I could again write out what I want. I want the percent of x's that are less than 21, but that's optional. What really matters is that I standardize. I take the number I care about, that 21 cutoff, I subtract the mean, I divide by the standard deviation. 21 minus 16 is 5, divided by 4 is 1.25. Again, we don't have to round because our standard deviation was very beautiful. Okay. So if we want, we can rewrite this in terms of our z. And I'll even draw the whole entire new picture. Our new mean is 0. That was 16 became 0. 21 became 1.25. And we still want everything less. And so we can see that it matches what we're looking for. So now that we have our standardized version, we go to our table and we look up 1.25.